everyone, welcome to another episode of Data Structures and Algorithms. In this episode, I'll be explaining about complete binary trees. So before we dive into what a complete binary tree is, we need to understand a binary tree. So a binary tree is a non-linear and a hierarchical data structure that has two child nodes at most. So which are referred to as the left child and the right child. So in the given picture, A is the root of the tree, which is at the top of the tree, and B and C are the child nodes of A. B is the left child and C is the right child. So BDE, if you consider BDE, it is a subtree of the given tree, and KLMNOP are leaf nodes, which are nodes that do not have any children. What is a binary tree? A binary tree is a special type of binary tree where all the levels are filled completely except the last level, and all the nodes are as left as possible. So if we talk about the properties of a complete binary tree, there are three main properties that we should know about. So the first one and the most important one is that all the levels except for the last level must be completely filled, and all the nodes must appear as far left as possible, and non-leaf nodes must only have two child nodes. So if we consider this tree, A is the root of the tree and B and C are child nodes of A. So the first point is that all the levels except for the last level must be completely filled. So in this tree, the last level is BEF level, and BC, and the BC is the last level before the last level. So the BC level is completely filled except for the last level, that is the EDEF, and it's missing a one, so it's not completely filled, which satisfies the first property. And the second property is that the nodes must appear as left as possible. So all the nodes are as left as possible. The F is in the left side, which it could have been in the right side too, but then it's not a complete binary tree. So because of this, it's a complete binary tree. And the third one is that non-leaf nodes must only have two child nodes. So in this, the non-leaf nodes are B and C, and B and C have two child nodes. Only C has one because the last level is not completely filled. So if we compare complete binary tree with a full binary tree, there are several features that may differ. So as we talked before, in a complete binary tree, all the levels except for the last level must be filled, and the leaf nodes or all the nodes must appear as left as possible, and the non-leaf nodes must consider at most two nodes. So in a full binary tree, every node must have either 0 or 2 children. You can't just have one child like the complete binary tree. So if we compare a perfect binary tree and a complete binary tree, so now we all know the properties of a complete binary tree. The way it differs from a perfect binary tree is that all the internal nodes must have two children and all the levels must be filled. Like you can't have one or 0 children in any level. It must be completely filled. That's what is called a perfect binary tree. So if we are given an array and to make it convert that into a complete binary tree, so I'll explain to you how to do it. So 0, 1, 2, 3 are the indexes of the array, and 10, 20, 10, 7, 3, 9 is the data of the array. So to find the left child of a node, we have an equation called 2i plus 1. I is the index of the node that we are going to find the left child, and to find the right child we just have to add 2 instead of 1, so it's 2i plus 2. So if we are think of, we are going to find the parent of a certain node, find that we have to use this equation, which is I minus 1 divided by 2. So let's just find the left child of 10. So the index of 10 is 1, so 2 into 1 plus 1 is 3. So this at the third index, there's it's the second, so 2 is the left child of 10. So now I'll show you an example on how to do it, how to do another one. So this is the example we are going to try out. We are going to find the parent, left child, right child, and the grandparent of the node 2. So here's the array and these are the indexes. First we find the left child. So we find the left child. The equation is 2i plus 1. So index of 2 is 3. So you're gonna write 2 into 3 plus 1. So 2 into 3 is 6 plus 1 is 7. So the left child of the node 2 is in the 7th position. So let's mark it. The left child of the node 2 is in the 7th position, which is the left child is 8. Left child is 8. So now let's find the right child of the node 2. When you find the right child, we just have to add 2 instead of 1. So 2i plus 2. So 2 multiplied by the index of 2 is 3, and we add 2. So 2 into 3 is 6 plus 2 is 8. So the right child of 2 is in the 8th position. So let's mark that. It's in the 8th position. Now we have to find the grandparent of 2. So when you find the grandparent of 2, we are just going to use this last equation. Find the grandparent. So this is the equation. We are saying it as grandparent because the 2 is a parent that we used to find the left child and the right side. So we have to find the parent of the node 2, so which is equals to the grandparent. So let's I is the index of 2 is 3, 1 minus and 2. So 3 minus 1 is 2 divided by 2 is 1. The grandparent or the parent of the node 2 is in the position 1. So 10 is the parent of 2. So we use in real life we use complete binary trees in heap sort based data structures, and things like that. So that's and those are the applications that we use complete binary trees in real life.